I'm Saritha Kumari, Assistant Professor in EEE Department, working at Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today, my topic is inductance of three-phase unsymmetrically placed transmission line. So basically, in my previous lecture, we have seen single phase line. For a single phase line, the inductance for a single circuit, single phase line, and a composite single phase transmission line means a standard single phase transmission line. So composite means we know that there are multiple conductors for one phase. So that is a standard conductor. That may be a double circuit, okay, like that. So now we see the inductance for three-phase line. So that is unsymmetrical three-phase line means the three-phase line means we know that basically there are three conductors. So then unsymmetrically spaced means the distance between the conductors is unequal. So that's why it is named as unsymmetrical. The conductors are with unequal distances between them. If we say conductors A, B, C are 1, 2, 3, the distance between the conductors from one conductor to another conductor is different. Unsymmetrically placed transmission line. So again, this topic comes under course outcome 1. So here we can see in the diagram this three-phase unsymmetrically spaced line where there are three conductors shown with small a, small b, small c, the three conductors, and the distances between them you can see clearly. Between the AB conductors the distance is capital D suffix AB, and conductors BC is D suffix BC, and conductor CA the distance is capital D suffix CA. Now the radius of the each conductor is smaller. It is same. The radius of the three conductors is same, which is R is taken. Then the distances already I mentioned. Distances between the three phases is given in sequence. First between if we say conductors are ABC, the distances also between the phases DAB, DBC, DCA. Now, the flux linkages. If we write the flux linkages expression for the three conductors. So, first we write the flux linkages for the conductor A, which is denoted with psi A, which is given by, this is the expression. So, from my previous class, you understand this, how it is written. So the flux linkages of one conductor when there are neighboring conductors are there whose currents are different. So here first flux linkages of conductor A, which is psi A, 2 into 10 power minus 7 in brackets. So Ia into log base E 1 by R dash. This is with respect to its own current. Okay. Current of that conductor is Ia. A conductor has a current Ia, and related to based on its radius, own radius, it is given by the term log of 1 by R dash. Okay, R dash means we know that 0.7788 into R. Next, due to the nearby two conductors B and C. So, side conductors. So, conductor due to current conductor in B, the current is IB. Due to that, IB into log of 1 by distance between conductors AB, that is DAB. Okay. Next, due to phase C, IC into log of between, if you see the diagram also, you can understand, between conductors AC the distance is DCA, right? So IC into, that's why IC into log of 1 by DCA. Say that equation 1. In the same manner, flux linkages of conductor B and also conductor C is written. So, psi B is equal to 2 into 10 power minus 7. Due to its own current IB, the term is IB log of 1 by R dash, and due to the neighboring conductors A and C. So, if we see for conductor B, due to current conductor A, IA into log of 1 by DAB. Then due to conductor C, IC into log of 1 by DBC. Next, that is equation 2. Next, similarly, flux linkages of conductor C. So, 2 into 10 power minus 7 due to its own current IC into log of 1 by R dash. Then C is linked with the two remaining two conductors. That means it is just nearby conductors, remaining two phases AB. That's why due to A, conductor A, IA into log of 1 by DCA. Next, due to other one B, IB into log of 1 by DBC from the diagram, right? So from the diagram for C, the two conductors, its related distances. So that is how the flux linkages expressions are written. Next, here to get the inductance expression, finally we want to write the inductance expression. But if we see in the flux linkages expression, there are three currents which are related to its phases. So IA, IB, IC. So in order to get the relation between them, IA, IB, IC, so consider for a three-phase system, we know that basic from the basic knowledge. In case of a three-phase circuit, if we consider the three phases like this, A, B, C, depending upon the direction we take, it may be clockwise or anti-clockwise. The angle between the any two phases is 120 degrees. Now we start with one phase which is taken as reference. Generally, we take phase A as reference. So then IB is given by, in terms of IA, we can write IB. So here you can see IB is equal to a constant is shown alpha square into IA. So that means basically IA is taken as, let us say, 1 at an angle of 0 degree. Then IB is written as from this. Okay. So IB is written as, IB is, we can see if we go in clockwise, it is 120 degrees, right? So IB we can say 1 at an angle of 120. Okay, but if we come in the anti-clockwise direction, this direction, okay, we can say that IB is displaced by 240 degrees, right? So so here that is the direction taken. So IB is given by 1 at an angle of 240 into IA. Okay, so that is how it is written. So where alpha is, okay, 240 represents 240 degrees. Okay, and its magnitude is written in terms of J operator like this. E power J 240 is nothing but minus 1 by 2, minus 1 by 2, this is minus. Okay, so that means we know that e power J theta is nothing but cos theta minus j sin theta. So that is how e power j theta, it is minus, I think. So it is written. So cos theta is here minus 1 by 2, and sin theta is minus j root 3 by 2. So that is what alpha square value. Next, IC is given by the clockwise direction, anti-clockwise direction is taken. So IC is given by how much angle? 120 degrees. That's why it is written as alpha into IA. So IC displaced by 120 degrees from IA, and IB is displaced by 240 degrees from IA. So that is how we consider the relation between IA, IB, IC currents here. So here alpha value is given by e power j 120. So that is value is given by uh, so it is plus only. So e power j 120 value is minus cos theta plus j sin theta, right? So minus 120 plus j root 3 by 2, right? So that is how the uh, alpha value is written, mentioned. So based on this relations, um, so previous flux linkages, previously whatever the expressions we have, psi a, psi b, psi c, so in that substitute for IB and IC in terms of IA. Okay. And finally, we get the psi A expression only in terms of IA after substituting like this. Okay. So then, if we write the inductance, so we know that inductance is given by flux linkages by current. So here, if we are writing inductance in phase A. So psi A by IA. So finally, current IA gets cancelled. The expression for LA is given by in terms of alpha and alpha square like this, right? So 2 into 10 power minus 7 log of 1 by r dash plus alpha square log of 1 by DAB. Okay. So just in terms of IB and IC, in place of IB and IC, we have written that IB/IC in terms of IA. So IA gets cancelled. So finally, this is the expression for LA, inductance, okay, of conductor A. Similarly, inductance of conductor B also mentioned in the same manner. Okay, so here, uh, then here um, we substituted IB/IC. Okay, sorry, IA/IC. So from the above relations only. So this is the expression for LB, inductance of conductor B, and also similarly inductance of conductor C. Okay, so this is for a three-phase unsymmetrically spaced transmission line. Okay, so from these expressions, we we can understand that the three conductors, okay, the three conductors of the three-phase line, means the conductors ABC, the inductances are unequal, right? The inductances are unequal, uh, which, okay, which is undesirable. So that is what it is mentioned here. So which is what undesirable, as the result in unbalanced circuit configuration. Okay, so we'll see few more points because of this unequal inductances here in the three-phase line, unsymmetrical spaced line. What are the drawbacks? Few more drawbacks also there. So because of this, so how to eliminate this? Okay, to avoid this situation, um, they introduced a topic, they introduced a concept which is called transposed line, which is the transposition. Okay, the concept is transposition. Okay, so here, uh, the figure, we can see a three-phase unsymmetrical line, the same thin three-phase line. Previously we have seen the same three-phase conductors ABC only, but here just distances are shown with different letters. So here, distance between the first two conductors, okay, is D12, means AB. Next distance between the conductors BC is, okay, means second third conductors D23. Next, similarly between CA is 31, D31. So this is what they have considered the three-phase circuit. So here, there is no neutral wire. So let us say there, okay, it is mentioned that, assume that there is no neutral. Then we can say that IA plus IB plus IC is equal to 0. A balanced system, right? A balanced three-phase circuit. If there is no neutral current, so sum of the three currents is equal to, three-phase currents is equal to 0. IA plus IB plus IC is equal to 0. Now, they're talking, because of that unequal inductances, okay, what will happen? So the first thing is, the asymmetrical spacing causing flux linkages, therefore inductances of each phase to be different, resulting in unbalanced receiving end voltages. This is the first point. Okay, unbalanced receiving end voltage. Transmission line, for the transmission line, okay, sending end is the generating station or a substation where the voltage is constant, right? We are getting, for a three-phase supply, 415 440 volts. Okay, so that is fixed, there is no change at the sending end. Okay, so at the receiving end, who is there? A consumer, that may be a domestic consumer or an industrial consumer. Okay, that will not going to be 415 volts if we say a three-phase AC. Okay, so we'll get a undesirable voltage. Okay, because of this unsymmetrical spacing. Okay, because of that, that means unequal inductances, that is the reason. Okay, so next, what is the second point? Also voltages will be induced in the adjacent communication lines. Okay, that is the second drawback. There will be voltages induced in the adjacent communication. So the transmission lines are projected on the transmission towers. Okay, beside that, communication lines also passing. Okay, so this unequal inductances causes undesirable, okay, voltages. They induce okay, undesirable voltages. Okay, that is a second drawback. So to handle this, okay, to overcome these problems, they introduced this concept called transposition. Okay, so what is meant by this transposition? Okay, here in the transposed line, suppose let us say if a line is transposed, then here each conductor takes the all the positions. There are three positions. Okay, so in transposed line, each conductor takes all the three positions of the line. Here each position is given by one third of the total length of the line. Okay, that is transposed line. Okay, so I will show you that then you will understand. So this is a transposed line, this arrangement. Okay, you see the diagram. So there are positions. Okay, three positions, one, two, three, and total length of the line is, let us say, small l. Okay, so transposed line means, okay, as I mentioned just now, each conductor takes all the positions of the line. Each conductor takes all the positions of the line. Here, each position is a one third of the total length of the line. Okay, so each position, this is one position, this is another second next position, this is a next position. So first position length is L by 3, and this position also length is L by 3, and third one also L by 3. So that is what. So here see that in the first position, here conductor A is there, second position B is there, C is there. In the next position, conductor A, okay, move to next place. Okay, then B move to the next place. So that's why it is shown like this. It came, okay, down, one level down. A, B, and C goes up. Okay, and next line, A comes next down level. So next A comes here. Then B goes up, C comes next level. So that is what transposal line means. Each conductor takes all the positions of the line. Here each position length is a one third of the total length of the line. Okay, so if L is the length, then each position length is L by 3, right? So I hope you understood. So this is what transposal line. Transposal line. Okay, so what will happen? See that this arrangement causes each conductor to have the same average inductance for the transposition line cycle. Okay, this causes same average inductance. Okay, now over the length of the transposition cycle, the total flux linkages and hence net voltage induced in the nearby communication line is 0. Okay, so because of that, the voltage is induced in the communication lines also 0. Okay, so now if we see the look at the expressions for flux linkages for the first section. So this is the first section, let us say, right? um, Second section, third section. So first section, the flux linkages of conductor A is given by 2 into 10 power minus 7 Ia into log of 1 by its own radius Ra dash plus Ib into log of 1 by distance between conductors 1 and 2, first two conductors, right? So 1 by D1 2. From the previous diagram, we have taken the three conductors, different distances between them are shown in terms of d1 to d to 3d 3 1. Okay, based on that. So then distance between the conductors AC is log of 1 by IC into log of 1 by d31. Okay, so Weber turns per meter. Next, similarly for the second section, psi A2. Okay, so for this second section, psi A2 is given by, okay, that means flux linkages of conductor A when it is in second position. So 2 into 10 power minus 7 Ia log of 1 by Ra dash due to its own. Then due to B, conductor B, IB into log of 1 by, now it is in second position, right? So 1 by D23 and uh, then IC into 1 log of 1 by D12. Okay, because it is in second position. So what are the near beside conductors related distances? Okay, D23 and D21 are 1. Next, similarly, when it is in third section, okay, this is the third section, right? This is in third place now. Okay, then its own radius component next related to the remaining 3 1 and 3 2, right? So that is how the flux linkages of the conductor A in each position. Now, the average flux linkages of conductor A is given by psi A1 plus psi A2 plus psi A3 by 3. So, adding the three equations, so this is a final equation 2 into 10 power minus 7 into IA into log of 1 by RA dash plus IB into log of 1 by, there are with IB there are three terms, so which are log A into log A plus log B plus log C means log ABC, right? So that's why the three terms are multiplied. Similarly, with respect in terms of IC, we have the three terms. That's why three terms we can see here. Now here for a balanced system, we know that IA plus IB plus IC is equal to 0. That's why IB plus IC is can be taken as minus IA. So because here this term is same, right? So the IB plus IC is replaced with minus IA. So the above expression becomes, okay, 2 into 10 power minus 7 into IA into log of D1 to D2 3 D3 1 whole power 1 by 3 by RA dash. Here D equivalent is equal to, okay, Q D1 to D2 3 D3 1 whole power 1 by 3, that is equivalent equilateral spacing. Okay, so finally the expression for LA is given by psi A by IA, right? So that's why IA gets cancelled. So 2 into 10 power minus 7 log of D equivalent by RA dash. So what is that RA dash? We know that self GMR, right? Self GMR. Okay. So this RA dash. Self GMR. So which is denoted with DS. So dq by finally expression is given by this one. Next, we also know that this in the numerator, this D represents always mutual GMD, which is denoted with DM, right? From my previous lecture. So, the mutual GMD between the three conductors in the three-phase line. Now, if RA is equal to RB plus if RA is equal to RB is equal to RC, okay, that means if the three conductors of the three-phase line have the same radius, then automatically inductance is also the same expressions. LA is equal to LB is equal to LC. So this is a expression for inductance in case of a three-phase line with transposition. Okay, inductance expression for a three-phase line with transposed line. Okay, with the transposition. Okay, so if you remember, this expression is same as the single phase line inductance expression, right? Only the thing is here we have numerator, this D is equal to cube root of the three distances. Okay, distances between the conductors in that given three phase line, and DS is same as a single phase transmission line. So this is the expression for inductance of the three phase transposed line. So these are my references. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.